We have another characterization of connectedness. Connectedness in a topological space, and this is known as the basic theory of connectedness. This is also known as the basic theory of connectedness. The first characterization of connectedness was that a topological space X is connected if and only if its closed and simultaneously open sets are what? Empty set, and the set itself. X is closed, X is connected if and only if the only open sets of X are X and the empty set itself. So here we are saying that X is connected if and only if there exists no continuous map from X onto the discrete two-point space. So we want to prove this. I think we are going to, it's an if and only if statement, so that one follows in two ways. So we are going to prove the forward direction. We are going to prove the forward direction. But before we prove the forward direction, we are going to first define what a discrete two-point space means. What a discrete two-point space means. So we are going to let, this is a definition. We are defining a discrete two-point space. So a discrete two-point space is a pair. Discrete two-point space is a pair Y with the topology tau. Discrete two-point space is a pair, that one, where Y is equal to, Y is made up of only two elements, 2 points, and this topology, the discrete topology on Y. The discrete topology consists of subsets of Y. So here we have subsets of Y, the power set of Y, we have the empty set, we have A, we also have B, then we also have Y itself. Those are the open sets there. So that is a discrete two-point space. Now we are going to proceed with our proof. So we are going to prove the forward direction. Suppose that X is connected, then we prove that there exists no continuous map from X onto the discrete two-point space. So how are we going to prove this? We are going to show that I think it's contrapositive, X not connected. We are going to suppose that X is not connected, and this should imply that there exists a continuous map. We are going to follow that argument. If we can prove that, then this will imply that X connected implies that there exists no continuous map. So we are going to suppose that X is not connected. Suppose that X is not connected, then there exists then it has a separation. There exists A and B open sets in X, whereby these sets are non-empty, they are distinct, and they are disjoint, and they form a separation of X. They form a separation of X, which is A union B. Suppose that X is not connected. So we are going to show that there exists a continuous map. We are going to define a map. There exists a continuous map from X onto the discrete two-point space. We are going to define a map and then show that it's continuous. X is now separated. You have to observe that X is separated. So it's like we are having A and B. This is B. this is A. Now X is the union of A and B. Now this is my X here. This is my X, the union of this. I want to define a map from X. I want to define a map from X onto a discrete two-point space. I want to define a map from X onto a discrete two-point space, which is Y. Which is Y having sets A and B. But this is a separation. So how are we going to define this map? So define a map from X onto the discrete two-point space Y by f of X equals, f of X is A if A is in A, and we are having a separation, so it will be A if A is in A, and it is B if B is in B. Now we show that this map is continuous. We show that F is continuous. We show that F is continuous. How can you show that a map is continuous? So in terms of open sets, we shall show that F is continuous. F is continuous if for each open set U in Y, if for each open set U in Y, the pre-image of U is open in X. The pre-image is an open set in X. So we are going to show that for each open set U in Y, open sets in Y are these ones. Compute the pre-image and show that they are open sets in X. They are open sets in X. We compute that. So we are going to start with what? With the pre-image. These are the open sets of Y. So the pre-image of the empty set, image of the empty set is an empty set. So an empty set is an open set in X. The pre-image of set A, pre-image of set A, you observe that pre-image of set A is A, which is an open set in X. A is an open set in X by our hypothesis. Also, the pre-image of B is capital B, which is an open set in X. I'm computing the pre-image of this, and this, then the pre-image of a space Y is equal to X, which is also an open set in X. So how am I computing these pre-images? The inverse. Remember, here I'm having open sets, the empty set, set A, set B, and Y. So the pre-image is the one which this is F, then the pre-image is the one taking this back. Yes. So the pre-image of this empty set is an empty set. Then the pre-image of A, remember f of X is A if A is in A. So what will be the inverse of set A? The inverse of set A will actually be capital A. Same applies to the inverse of set B. This set here. Yes. So each of those sets are open sets. The empty set is an open set. Set A is an open set. Open set X is also an open set. So we observe that. Observe that for each open set, U in Y, the pre-image of U is open in X, implying that F is continuous. So we have been able to show that X not connected implies that there exists a continuous map from X onto the discrete two-point space. So this further implies that X connected, X connected implies that there exists no continuous map from X onto the discrete 2-point space. So we are going to prove we are going to proceed with the other direction. Conversely, we are going to suppose that there exists no continuous map from X onto the discrete 2-point space. Then we show that suppose that there exists no continuous map from X onto the discrete 2-point space. We show that X is connected. We are going to follow via the same argument. We are going to prove that there exists a continuous map. X is a continuous map, and this should imply that X not connected. If you can do this, then we are done. If you can prove that, then we are done. So we are going to suppose that there exists a continuous map from X onto the discrete 2-point space. Now, if we are saying that map exists, we have to define that map, and we are going to define the same map. Suppose that there exists a continuous map from X onto the discrete 2-point space. We are going to define the same map we used in the first argument. So we are going to define this map. Define that map from X onto Y by what? By f of X equals A if X is in A. If X is in A, and also it's B if X is in B. Actually here I've just realized that this was supposed to be X. Kindly correct that. This was also supposed to be X. Yes, by definition of the pre-image. So define that map by that. What shall we have? Correct this. This was a wrong statement. So a map defined that way. We realize that a map defined in this way has A as the pre-image of the set A, and also B as the pre-image of set B. We want to show that X is not connected. We are trying to construct a separation of X. So moreover, A and B are non-empty. Those two sets are non-empty sets. Why are we saying that they are non-empty? The pre-image of within the pre-image of A, we have something, because this set is not empty. This set here is not empty. So similarly, B is not empty because this set here is not empty. So A and B are non-empty sets. You observe that they are also distinct. And A intersection B is equal to the pre-image of A intersection the pre-image of set B, and this is equal to the pre-image of A intersection B. This is equal to the pre-image. These two sets are not intersecting. pre-image of the empty set, which is an empty set. So A and B are disjoint. So this implies that A and B are disjoint. What else? Compute the union. A union B is equal to the pre-image of A union this. This is equal to F A then union B. That is equal to what? That is equal to F inverse A and B. So we have A union B as F inverse, then A and B. And this set A, and this set consisting of A and B was Y. If you remember, this was set Y. Pre-image of Y is X. So this implies that X is equal to A union B, where A intersection B is an empty set, where A is different from B. Also, A and B are non-empty. A and B are non-empty, implying what? Implying that X is not connected. We have been able to construct the separation of X. So this implies that we have been able to show that there exists a continuous map, implies that X is connected. There exists a continuous map, should imply that X is connected. So this implies that there exists no continuous map, should imply that there exists no continuous map, should imply that X is connected. Yeah, but I have realized that in the first part there, I made a mistake somewhere in defining the pre-images. So you can go back and recap that, because by definition, let me try to hear something here. The proof is done, but let me try to explain something. When I constructed the pre-images of A and B, I think I was constructing a pre-image of what? F of X was defined as it was supposed to be A and B if X is in A, and also B if X is in B. Yes. I think in the first part I used the A here and I used the B there. So kindly go and correct that information. This was wrong. The first one was wrong, where I used A and I also here I used B. Yeah, it was supposed to be X and X. Then if it's that case, then the pre-images will come out here. So kindly go and correct that, and I apologize for that mistake.